Have you ever wondered what time truly is? Is it an invisible river sweeping us through the shores of memory and hope, or merely a mirage our minds conjure to make sense of the universe's chaos? Picture this. You're standing atop a mountain, gazing down at a valley stretching endlessly before you, where sunlight dances on leaves, and for a fleeting moment, time seems to hold its breath. But what if you were racing at the speed of light, or spiraling into the grip of a black hole? Would that moment still mean the same? Welcome to a journey into the nature of time, a concept as familiar as the beating of your heart, yet as enigmatic as the stars glimmering beyond the horizon. In the realm of physics, time is more than a sequence of ticking seconds. It's a dimension, the fourth dimension, woven intricately with length, width, and height to form the fabric of the cosmos we call space-time. Albert Einstein, with a mind that soared beyond his era, revealed that space-time isn't a static stage where planets and stars play out their cosmic drama. It bends, it ripples, and most astonishingly, it shifts depending on who's watching. Imagine an astronaut hurtling through space at near light speed. For them, time slows to a crawl compared to someone rooted on Earth. When they return, their clock might show mere years have passed, while those left behind have aged decades. This isn't science fiction. It's the breathtaking reality of time dilation, born from the elegance of relativity. Yet time isn't just numbers on a dial or equations on a page. It challenges how we perceive the world, beckoning us to dream of voyages across epochs. Could we wind the clock back to mend our mistakes, or leap forward to touch days yet unborn? As physicists probe time's essence, they find it's neither fixed nor absolute. In every reference frame, with every velocity or gravitational pull, time tells a different tale. This fluidity transforms it from a dry abstraction into a gateway to infinite possibilities. A twin on a spaceship ages slower than their sibling on Earth. A clock near a black hole ticks at a languid pace compared to one far away. These aren't quirks, they're windows into a universe where time dances to the rhythm of motion and mass. So join me as we step through that gateway, where science and imagination intertwine. We'll unravel not just what time is, but how it shapes the very fabric of our existence. From the ticking of a second to the stretching of eons, time is both our companion and our mystery, a thread tying us to the stars, yet slipping through our fingers like sand. Let's chase it together through the wonders of space-time and see where its currents take us. Delving into quantum mechanics, a new perspective on time. In the heart of modern physics, where the tangible dissolves into the probabilistic, quantum mechanics emerges as a governing principle of the very small. It is a theory that does not merely modify our understanding of reality, it revolutionizes it. Time, once an immutable backdrop against which all events unfold, begins to lose its classical coherence when examined through the lens of quantum theory. The certainty of past, present, and future, so deeply embedded in human intuition, yields to a reality where these distinctions blur, where particles transcend singular states, and where cause and effect entangle in ways that defy conventional logic. At the core of this quantum enigma lies the principle of superposition, the idea that a quantum system does not simply occupy a single state, but rather exists in multiple states at once. Schrödinger's famous thought experiment, in which a cat is both alive and dead until observed, serves as a metaphor for this strange duality. In a classical world, time is a linear progression, moving forward in a well-defined sequence. But within a superposed system, events exist simultaneously, seemingly independent of a singular temporal flow. The distinction between before and after dissolves, leaving us with an unsettling question. Is time truly fundamental, or is it an emergent property of a deeper, hidden reality? Even more profound is the phenomenon of quantum entanglement, in which two particles, no matter how far apart, remain inextricably linked. A change in the state of one instantaneously affects the other, a connection that appears to transcend the classical constraints of space and time. This eerie simultaneity suggests a universe where time may not be the independent parameter we perceive it to be, but rather a construct emerging from a deeper order, one where separations in time are as illusory as separations in space. If quantum mechanics is correct, and all experimental evidence suggests it is, then our conventional understanding of time may need to be reconsidered. Could it be that time, much like temperature or pressure, is not a fundamental aspect of reality, but an emergent property of deeper quantum processes? Could the apparent flow of time arise from the entanglement of information rather than being an intrinsic feature of the universe? These questions are not merely philosophical musings. They touch upon the very foundation of physics, from the birth of the cosmos to the structure of consciousness itself. As we venture deeper into the quantum realm, we stand on the precipice of a paradigm shift. The rigid, mechanical universe envisioned by Newton and even the relativistic space-time of Einstein may give way to a reality governed by probabilities, correlations, and an intricate web of quantum information. To understand time, we must first embrace the unsettling notion that it may not exist in the way we have always believed. Instead, time may be a thread woven from the very fabric of quantum interactions, an emergent symphony arising from a deeper, as yet unseen harmony of the universe. Quantum time travel, possibilities and paradoxes. Time travel has long been the realm of science fiction, a tantalizing fantasy where past and future become accessible like pages in an open book. Yet, as our understanding of quantum mechanics deepens, what was once mere speculation is now creeping into the domain of theoretical possibility. Could the fundamental principles of quantum physics provide a pathway to traverse time, allowing us to rewrite history or glimpse the unwritten future? If time travel is possible, even in the quantum sense, then the very nature of causality, reality, and human existence must be reconsidered. One of the most promising avenues for time travel emerges from the peculiar realm of quantum entanglement and retrocausality, phenomena that challenge our classical intuition about the unidirectional flow of time. In entangled systems, two particles, no matter how distant, share an instantaneous connection. This has led some physicists to speculate whether information might be transmitted backward in time, creating a bridge between past and future. Additionally, certain interpretations of quantum mechanics, such as the transactional interpretation, suggest that quantum events involve waves propagating both forward and backward in time, subtly hinting at the possibility of influencing the past. Yet, as with all grand ideas, time travel is fraught with paradoxes. The grandfather paradox, a scenario where one travels back in time and prevents their own ancestor from existing, illustrates the logical contradictions inherent in unrestricted time travel. If an action in the past alters the conditions necessary for the time traveler's own existence, how could they have traveled back in time in the first place? Some theories, such as the many worlds interpretation, offer a way out, suggesting that altering the past merely creates a new branching timeline rather than modifying the original. If true, this would mean that time travelers do not actually change history, but rather step into an alternate version of it. If even a limited form of retrocausality were achievable, our perception of history would no longer be fixed. Could we send quantum signals into the past to warn against catastrophe? Could a future civilization transmit knowledge back in time, altering the course of human progress? These are not merely academic musings, but questions that push the very boundaries of physics, touching upon the deepest mysteries of determinism, free will, and the structure of reality itself. The pursuit of quantum time travel is more than an exploration of physics. It is a challenge to the very fabric of our understanding. Whether time is an immutable river or a malleable construct remains to be seen. But one thing is certain: if quantum mechanics holds the key to time travel, then the universe is far stranger than we ever imagined. Time, the invisible thread that weaves the fabric of our existence, is often perceived as an unceasing flow, an unstoppable river carrying us from past to future. Yet, beneath this seemingly intuitive perception lies a profound mystery. Is time truly a continuous sequence, or is the present moment the only point of true existence, with the past and future as mere abstractions? While classical physics treats time as an immutable dimension, quantum mechanics suggests a far stranger reality, one where the past and future may not be rigidly fixed, but exist as probabilities, only materializing when observed. If this is true, then what does it mean to exist in the present? Could it be that the present moment is not simply where we experience life, but where reality itself is actively shaped? Throughout history, philosophers and scientists alike have grappled with the nature of time. In classical physics, Newtonian mechanics described time as an absolute backdrop against which events unfold, independent of human perception. In this view, the past is a set of completed events, and the future is a predetermined path waiting to be realized. However, Einstein's theory of relativity disrupted this notion, showing that time is not absolute but relative, dependent on the observer's frame of reference. According to relativity, time dilates at extreme speeds and in strong gravitational fields, meaning that what one observer perceives as the present may not be the same for another. Yet, while relativity suggests that time is malleable, it still treats it as a continuous entity. Quantum mechanics, on the other hand, presents an even more radical picture, one in which time may not flow at all in the way we assume. Quantum superposition, the principle that particles exist in multiple states until measured, implies that reality is fundamentally probabilistic. If the future is not predetermined, but exists as a set of possibilities, then can we say that it truly exists before it is observed? Similarly, quantum retrocausality, a controversial yet mathematically consistent concept, suggests that present choices may influence past events at a microscopic level. If true, this would indicate that the past itself is not as fixed as we assume, but is also a set of probabilities that only collapse into certainty upon interaction with the present. If past and future exist only as probabilities, then the present moment becomes the point where reality is actively constructed. The famous double-slit experiment provides a striking example of this. When particles such as electrons are sent through two slits, they behave like waves, suggesting that they travel through both slits simultaneously. However, when a measurement is made to determine which slit the particle goes through, it suddenly behaves like a particle, and its wave-like properties disappear. In other words, the act of observation determines the outcome. This phenomenon suggests that the state of reality is not fully defined until it is measured, a principle that some physicists extend to time itself. If our observation is what collapses potential futures into a singular lived reality, then the idea of time as a pre-existing path may be an illusion. The past, too, may not exist in the way we typically assume, but instead emerges in relation to the present. The block universe theory, a concept in modern physics, posits that past, present, and future all exist simultaneously as a four-dimensional structure. But in the quantum realm, this view is challenged by the fact that past events may not be rigidly recorded, but could remain subject to later influences. Living in the present, the intersection of science and philosophy. These ideas are not purely theoretical, they have profound implications for how we live our lives. If only the present moment is truly real, then the weight of past regrets and future anxieties begins to dissolve. In a quantum world where the past is not fixed and the future is still unwritten, we are granted an extraordinary freedom, the ability to shape reality not through deterministic chains of cause and effect, but through the choices we make now. Throughout history, Eastern philosophical traditions have emphasized the importance of present moment awareness. Buddhism, Taoism, and mindfulness practices have long taught that clinging to the past or worrying about the future blinds us to the reality of the present. Remarkably, modern physics seems to echo these ancient insights. If quantum mechanics suggests that reality is constructed in the now, then perhaps the wisdom of living in the present is not just a matter of subjective well-being, but a reflection of the deepest truths about the nature of time itself. Yet, embracing the present is easier said than done. Our minds are naturally inclined to dwell on past events and anticipate the future. However, just as quantum experiments show that observation influences outcomes, perhaps our focus, where we direct our attention, shapes not only our psychological experience, but reality itself. If the past is not rigid and the future is a field of probabilities, then the present is not just where we live, it is where we create. The more we explore the paradoxes of time, the more it seems that the present moment is the only point of actual existence. While memory allows us to reconstruct the past, and imagination enables us to anticipate the future, both are mental constructs, representations, not realities. If quantum mechanics is correct, then the past exists only insofar as it remains entangled with the present, and the future is a vast, uncollapsed set of probabilities waiting for observation to give it form. This perspective shifts not only our understanding of time, but our entire way of being. Instead of seeing life as a linear journey from birth to death, dictated by an inexorable march of time, we can begin to see it as a series of unfolding presents, each moment rich with the potential to shape what comes next. This does not mean the past is meaningless or the future should be ignored, but rather that our primary focus should be on how we engage with the now, the singular point where existence and consciousness meet, where reality is not merely experienced, but created. The future of time, unraveling the mysteries. Time, an ever-present yet elusive force, has long perplexed scientists and philosophers alike. Is it a fundamental property of the universe, woven into the very fabric of reality, or is it merely an emergent phenomenon, a construct of human perception? As our understanding of physics deepens, so too does our recognition of time's mysteries. Quantum mechanics, with its counterintuitive principles of superposition, entanglement, and non-locality, suggests that time may not be the rigid linear entity we once believed it to be. Instead, it may be malleable, dynamic, and even subject to influence in ways that defy classical logic. The quest to unravel time's secrets is far from over. In the coming decades, advancements in quantum theory, relativistic physics, and cosmology may redefine our most fundamental assumptions about the nature of past, present, and future. Could time be an emergent property arising from deeper quantum structures? Could it be possible to manipulate time, not merely as an abstract mathematical concept, but as a tangible aspect of reality? As we stand on the precipice of scientific breakthroughs, we find ourselves grappling not only with equations and experimental results, but with the profound philosophical implications of what it means to exist within time. Since the days of Newton, time has been treated as an absolute entity, an unchanging background against which the universe unfolds. This view was profoundly challenged by Einstein's theory of relativity, which demonstrated that time is not universal but relative, stretching and contracting depending on gravity and velocity. Time, in this view, is intertwined with space, forming a four-dimensional continuum known as spacetime. Yet, relativity, despite its elegance, still treats time as a dimension, much like space. It does not fully explain why time appears to flow, or why we perceive a distinct separation between past and future. Here, quantum mechanics introduces an entirely new set of questions. Unlike classical systems, which evolve in a predictable manner, quantum systems exist in superpositions, where multiple states coexist until measured. This raises an unsettling question. If the future exists as a probability distribution, does it already exist in some sense, waiting to be collapsed into a definite reality by observation? Similarly, if quantum retrocausality is real, the idea that present choices can influence past events, then what does that say about the very structure of time itself? Physicists are now exploring these questions with increasing precision. Cutting-edge experiments in quantum computing, entanglement, and wave function collapse may soon provide empirical evidence to support or refute these radical interpretations of time. If time is indeed a product of deeper quantum phenomena, then future discoveries may lead us toward an entirely new framework, one where time is not an immutable feature of the universe, but a fluid, emergent quality shaped by quantum interactions at the smallest scales. With the rapid evolution of quantum mechanics and theoretical physics, several key discoveries could revolutionize our understanding of time in the near future. One of the greatest unsolved challenges in physics is the unification of general relativity with quantum mechanics. Many physicists believe that a successful theory of quantum gravity, such as loop quantum gravity or string theory, will reveal new insights into the nature of time. Some proposals suggest that time itself may be an emergent property arising from quantum entanglement rather than being a fundamental feature of reality. Recent discoveries in quantum physics have introduced the concept of time crystals, states of matter that exhibit periodic motion without energy loss. These bizarre systems challenge traditional notions of thermodynamics and could provide deeper insights into the nature of time symmetry. If time crystals exist in nature beyond controlled laboratory conditions, they could offer empirical evidence that time, like space, possesses hidden structures yet to be uncovered. While time travel remains speculative, some physicists are designing experiments to test retrocausality, the idea that future measurements can influence past quantum states. Certain interpretations of quantum mechanics, such as the transactional interpretation, suggest that particles may send signals both forward and backward in time. If confirmed, this could radically alter our understanding of cause and effect, potentially paving the way for novel technologies that manipulate temporal sequences at a quantum level. The scientific pursuit of time's nature is not merely an academic exercise. It carries profound philosophical implications, particularly in the realm of consciousness and free will. If the future exists as a quantum probability wave, does that mean our choices are predetermined, or do we actively shape reality with each decision? If retrocausality is real, could our present thoughts and actions ripple backward through time, subtly influencing past events? Perhaps most intriguingly, time travel, long relegated to the domain of science fiction, becomes a serious topic of philosophical and physical inquiry. Classical paradoxes, such as the grandfather paradox, have been challenged by new models of quantum mechanics. Some theories suggest that rather than altering the past, time travelers would enter branching timelines, meaning that each change results in a parallel universe rather than a modification of the original. This aligns with the many worlds interpretation, which proposes that every quantum event spawns multiple realities. The implications of time travel extend beyond mere physics. If it were possible to traverse time, even in a limited sense, it would challenge the very fabric of human experience. Would knowledge of the future alter our perception of destiny? Would awareness of multiple timelines expand or diminish our sense of agency? If we could send information to the past, how would history itself be rewritten, not just in books, but in our collective memory? As we look ahead, the pursuit of time's secrets is one of the most profound scientific endeavors of our age. Whether through quantum computing, new interpretations of relativity, or breakthroughs in consciousness studies, the nature of time may soon be understood in ways previously unimaginable. It is possible that in the near future, we will no longer see time as a simple progression of events, but as a dynamic, interactive field, one that we are not merely subject to, but active participants in shaping. While time remains one of the greatest mysteries of the universe, its future is clear. It is a frontier waiting to be explored. And as we stand on the cusp of discovery, we may find that time itself is far stranger, more fluid, and more mysterious than we ever dared to dream.
Imagine a world where every decision, every chance event splits the universe into countless parallel realities. Each choice you make, no matter how small or insignificant it may seem, creates a new branch in the vast tree of existence. Picture yourself facing a life-threatening situation. In one universe you might not make it, but in another, you survive against all odds. Now, envision a reality where you always survive, branching off into a new universe each time you escape death. This means that for every perilous moment, there's a version of you that continues to live on. This captivating and somewhat unsettling concept is known as quantum immortality. It challenges our understanding of life and death, suggesting that consciousness might never truly end. It stems from the mind-boggling realm of quantum mechanics, the theory governing the universe at its smallest scales. Quantum mechanics reveals a world where particles can exist in multiple states at once, only settling into a single state when observed. Quantum immortality takes inspiration from a particular interpretation of this theory, the many-worlds interpretation, or MWI. This interpretation posits that all possible outcomes of a quantum event actually occur, each in its own separate universe. This interpretation suggests that every quantum event causes reality to split into multiple parallel universes. Each new universe is a reflection of the different possible outcomes of that event. Each split creates a new universe identical to the original up until the point of the split. From that moment on, each universe follows its own unique path shaped by the different choices and events that unfold. Could this mean that somewhere in a parallel universe, there's a version of you who has cheated death time and time again? A version of you who continues to live on, experiencing new adventures and challenges in an endless array of realities? The intriguing idea of quantum immortality. Quantum immortality at its core proposes a radical idea. Consciousness never truly experiences death. This concept is rooted in the many worlds interpretation of quantum mechanics, which suggests that all possible outcomes of a quantum event actually occur, each in its own separate universe. Instead, in any scenario where death is a possibility, our awareness shifts to a parallel universe where we survive. Consider a car accident. In one universe the crash might be fatal, but in another you might walk away without a scratch. In most universes you might emerge unscathed or with minor injuries. The idea is that your consciousness continues in the universe where you survive, no matter how improbable that survival might be. However, in a few, the accident could be fatal, but according to quantum immortality, you would never experience those fatal outcomes. Your consciousness would always find a way to persist. According to quantum immortality, your consciousness would simply continue in a universe where the accident wasn't fatal. This means that, from your perspective, you are effectively immortal. This continuous branching of universes applies to every quantum event, every moment of our lives. Every decision we make, every action we take, creates a new branch in the multiverse. With each tick of the clock, countless new universes are born, each representing a different outcome. This means that there are infinite versions of you, each living out a different possibility. This implies an infinite number of yous, each experiencing a unique trajectory through the vast multiverse. The concept of quantum immortality challenges our understanding of life and death, suggesting that our consciousness might be far more resilient than we ever imagined. To grasp the essence of quantum immortality, we need to delve into the heart of quantum mechanics and the many worlds interpretation. This interpretation challenges our everyday understanding of reality. In the quantum world, particles like electrons don't behave like the objects we experience in our daily lives. They exist in a haze of probabilities, occupying multiple states simultaneously. This is called superposition. The act of measurement forces these particles to choose a specific state. This is where the many worlds interpretation comes in. It suggests that instead of choosing one state, all possible states occur, but each in a separate, newly born universe. Imagine flipping a coin. In our everyday experience, it lands on either heads or tails, but in the many worlds interpretation, both outcomes occur. The act of the coin landing creates two universes, one where it landed on heads, and another where it landed on tails. This principle, when applied to the vast number of quantum events happening every second, leads to an incomprehensible number of universes constantly branching out. Each universe is as real as the other, forming a complex, interconnected multiverse. Quantum immortality takes this a step further. It postulates that our consciousness, intricately linked to these quantum events, rides this wave of splitting universes, always experiencing a universe where it continues to exist. Section 5. Life, Death, and the Quantum Dance. A new perspective. If the many worlds interpretation holds true, it paints a fascinating, albeit unsettling picture of life and death. Death, in the traditional sense, might not be the end. Instead, our awareness simply shifts to a universe where we continue living. This implies a form of existence that persists indefinitely, branching through the multiverse, experiencing an endless array of possibilities. It's important to note that this interpretation doesn't suggest we become invincible or immortal in any conventional sense. We would still experience life and its challenges, just in a reality where our consciousness persists. Despite its intriguing implications, the many worlds interpretation and consequently, quantum immortality, remain highly controversial within the scientific community. Critics argue that it's an extravagant explanation for quantum phenomena. The lack of any testable predictions makes it difficult to verify or falsify. many physicists prefer other interpretations of quantum mechanics that don't require the existence of parallel universes. However, proponents of the many worlds interpretation highlight its elegance and internal consistency. They argue that it provides a clean and parsimonious explanation for quantum phenomena, avoiding the need for arbitrary assumptions. The tantalizing concept of quantum immortality, while fascinating, presents a significant challenge. How do you test it? The very nature of the idea, relying on subjective experience in unreachable universes, makes it seemingly impossible to verify scientifically. We cannot interact with or observe these parallel universes. Even if we could, identifying the version of ourselves who supposedly survived a fatal event in another universe would be an immense, if not impossible, task. Furthermore, the ethical implications of any experiment designed to test quantum immortality would be profound and raise questions about the value of life and the nature of consciousness. Despite its lack of scientific verifiability, the concept of quantum immortality continues to captivate the imagination. It offers a glimmer of hope in the face of our inevitable mortality, suggesting that consciousness might not be extinguished, but rather continues on a different path. However, it's crucial to remember that this is just one interpretation of a complex and still developing field of science. It's a thought-provoking idea, but not one to base life decisions on. The true nature of reality, the mysteries of quantum mechanics, and the possibility of a multiverse remain open questions. Further research and theoretical advancements might one day shed light on these profound concepts. Whether quantum immortality proves to be a scientific reality or a captivating thought experiment, it highlights the remarkable nature of the universe we inhabit. It compels us to question our place within the vast cosmic tapestry and the nature of our own existence. The concept of quantum immortality, which suggests that consciousness could continue in a parallel universe after death, challenges our understanding of life and death. The pursuit of understanding these profound concepts is at the heart of scientific exploration. Scientists and researchers dedicate their lives to unraveling these mysteries, driven by an insatiable curiosity and a desire to push the boundaries of human knowledge. While we may never have definitive answers, the journey of seeking knowledge and unraveling the mysteries of the universe is a journey worth taking. Each discovery, no matter how small, adds a piece to the puzzle of our existence and brings us closer to understanding the cosmos. As we continue to probe the depths of quantum mechanics and the potential for parallel universes, we embark on a voyage of discovery that could reshape our understanding of life, death, and the very fabric of reality. This journey is not just about scientific inquiry. It is about the human spirit's relentless quest to explore, understand, and find meaning in the universe.
Quantum immortality. The very phrase hums with an intoxicating blend of scientific intrigue and fantastical speculation. It whispers of a universe where death, the ultimate curtain call, might be nothing more than an illusion. Imagine a reality where consciousness, intertwined with the very fabric of existence, navigates a labyrinth of endless possibilities, always finding a path where life continues. Could this be a glimpse into the true nature of our reality, or merely a seductive siren song of wishful thinking? The allure of immortality is ancient, woven into myths and legends across cultures. From the elixirs of ancient alchemists to the fountain of youth sought by explorers, humanity has always been captivated by the idea of living forever. Yet, quantum immortality offers a distinct flavor, one seasoned with the complex equations and perplexing principles of quantum mechanics. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action spawns a multitude of parallel universes, each with its own version of events. Imagine a maze with countless pathways, each leading to a different outcome. In one path you might meet your end, but in another you continue to thrive. This is the essence of quantum immortality, the idea that there is always a version of you that survives, no matter the odds. But is this tantalizing promise grounded in scientific rigor or merely a fantastical flight of fancy? The concept challenges our very understanding of reality, pushing the boundaries of what we consider possible. The allure of immortality is ancient, woven into myths and legends across cultures. From the elixirs of ancient alchemists to the fountain of youth sought by explorers, humanity has always been captivated by the idea of living forever. Yet, quantum immortality offers a distinct flavor, one seasoned with the complex equations and perplexing principles of quantum mechanics. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action, spawns a multitude of parallel universes, each with its own version of events. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action, spawns a multitude of parallel universes, each with its own version of events. But is this tantalizing promise grounded in scientific rigor or merely a fantastical flight of fancy? The concept challenges our very understanding of reality, pushing the boundaries of what we consider possible. To grasp the concept of quantum immortality, we must first venture into the perplexing realm of quantum mechanics. This field, often described as the foundation of modern physics, delves into the behavior of particles at the smallest scales. It's a world where the rules of classical physics no longer apply and where particles can exist in multiple states at once, a phenomenon known as superposition. At its heart lies the many worlds interpretation, a mind-bending idea proposing that every quantum measurement, every interaction on a subatomic scale, splinters our reality into a multitude of parallel universes. This interpretation, first introduced by physicist Hugh Everett in the 1950s, suggests that all possible outcomes of a quantum event actually occur, each in its own separate universe. In each of these branching realities, a different outcome unfolds. Imagine a tree where each branch represents a different possible future. As we move forward in time, we traverse one of these branches, but the other branches still exist, each representing a different version of events. Imagine flipping a coin. In one universe, it lands on heads, in another, tails. This simple act of flipping a coin creates two distinct realities, each as real as the other. The many worlds interpretation posits that both outcomes occur, each playing out in a separate, self-contained universe. The many worlds interpretation posits that both outcomes occur, each playing out in a separate, self-contained universe. This means that every decision we make, every random event, creates a new branch in the tree of reality, leading to an ever-expanding multiverse of possibilities. Applied to the concept of death, this interpretation suggests a startling possibility. While in one universe we might succumb to a fatal event, in another, our consciousness persists, having navigated to a world where we survive. This idea, known as quantum immortality, challenges our understanding of life and death, suggesting that our consciousness might continue to exist in a parallel universe where we avoid the fatal event. The allure of quantum immortality, while captivating, must be carefully examined through the lens of scientific scrutiny. This concept, which suggests that consciousness could continue in a parallel universe after death, is fascinating, but remains speculative without solid evidence. At the heart of the scientific method lies a fundamental principle: empirical evidence. This principle demands that any hypothesis or theory must be supported by observable and measurable data. Scientific theories, no matter how elegant or alluring, must find grounding in observable, measurable, and repeatable evidence. This process involves rigorous testing and validation, ensuring that the results can be consistently reproduced. This emphasis on empirical evidence is not a matter of mere academic formality. It's the bedrock upon which our understanding of the universe rests. It is through this meticulous process that we separate fact from fiction and reality from mere speculation. Without verifiable evidence, we drift into the nebulous realm of speculation and conjecture, where any idea, no matter how outlandish, can take root. This is why the scientific community places such a high value on empirical data. The history of science is littered with theories, once widely accepted, that crumbled under the weight of contradictory evidence. From the geocentric model of the universe to the theory of phlogiston, these ideas were eventually discarded as new, more accurate data emerged. This relentless pursuit of truth is what drives scientific progress forward. Herein lies the primary challenge facing the notion of quantum immortality: it remains firmly in the realm of the untestable. The very nature of the many worlds interpretation, while intriguing, presents a seemingly insurmountable barrier to verification. We are, by definition, confined to our own branch of reality. We cannot interact with or observe these parallel universes where our alternate selves supposedly persist. This inability to test or falsify the concept of quantum immortality renders it, at least for now, a philosophical thought experiment rather than a scientifically validated theory. It occupies a tantalizing gray area, a conceptual playground where science and imagination intertwine. Further complicating matters is the enigmatic relationship between quantum mechanics and consciousness. Some proponents of quantum immortality suggest that consciousness plays a role in the selection of which branch of reality we experience. This notion, while captivating, delves into territory where even established science treads cautiously. Consciousness, despite decades of research, remains one of the most profound mysteries of the universe. Its nature, its origins, and its relationship to the physical world are still subjects of intense debate and ongoing research. The very act of observation, of measuring a quantum system, seems to force it from a state of superposition, where it exists in multiple states at once, into a single, definite state. This is often referred to as the measurement problem in quantum mechanics. Whether consciousness plays a role in this collapse, or whether it's governed by other yet undiscovered mechanisms, is a question at the very frontier of our understanding. Until we unravel the mysteries of consciousness and its potential role in quantum phenomena. The connection between quantum mechanics and immortality will likely remain shrouded in speculation. The challenges in studying quantum immortality highlight a fundamental truth about the scientific endeavor. Testability is paramount. Theories, no matter how elegant or appealing, must be held to the rigorous standard of empirical verification. This commitment to testability is not a limitation but rather the very engine that drives scientific progress. It's what distinguishes scientific knowledge from mere belief or conjecture, while the allure of the unknown will always beckon. It's through the meticulous gathering and interpretation of evidence that we move from the realm of speculation to the solid ground of scientific understanding. So, where does this leave us with quantum immortality? It remains a captivating idea, a tantalizing what if that sparks our imaginations and challenges our understanding of life, death, and the nature of reality itself. However, in the absence of verifiable evidence and with the significant hurdle of testing such a concept, it remains firmly in the realm of speculation. This doesn't invalidate the concept, but it does place it outside the current framework of scientifically validated theories. It serves as a potent reminder that our understanding of the universe is constantly evolving. The story of quantum immortality, then, is not necessarily one of a definitive answer, but rather an ongoing exploration. It's a testament to the power of human curiosity, our relentless drive to explore the boundaries of knowledge and to grapple with the most profound questions of existence. While quantum immortality may never graduate from a captivating concept to a scientifically proven reality, the very act of contemplating it pushes the boundaries of our understanding and fuels the engine of scientific inquiry. And in that journey of exploration, in the relentless pursuit of knowledge, lies a beauty and wonder that transcends any definitive answer. Quantum immortality, a concept both exhilarating and terrifying. It challenges our fundamental understanding of life, death, and the nature of reality itself. Imagine a world where death is not the end, but a doorway to countless possibilities. This is the essence of quantum immortality, a mind-bending concept rooted in the strange and wonderful world of quantum mechanics. At the heart of this idea lies the many worlds interpretation, proposed by physicist Hugh Everett III. MWI suggests that every quantum measurement or event causes the universe to split. Each split creates a new world where a different outcome unfolds. In this grand tapestry of parallel universes, every possibility exists simultaneously. Quantum immortality takes this a step further. It proposes that while we may experience death in one universe, our consciousness persists in another where we survive. This endless cycle of near-death experiences across parallel worlds presents a profound challenge to our perception of mortality and the very fabric of our existence. The implications of quantum immortality are vast and far-reaching, touching upon the realms of physics, philosophy, and even our deepest existential anxieties. It compels us to confront profound questions about the nature of consciousness, the meaning of reality, and the ethical implications of living in a world where death is not the end, but merely a transition. To grasp the concept of quantum immortality, we must first delve into the mind-boggling realm of the many worlds interpretation. This interpretation of quantum mechanics, though controversial, offers a radical departure from our conventional understanding of reality. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once. When we measure a particle's state, the superposition collapses, and we observe only one outcome. MWI posits that this collapse doesn't occur. Instead, the universe branches off, creating separate realities for each possible outcome. Imagine flipping a coin. In MWI, both heads and tails exist simultaneously, each in a different universe. We, the observers, also split, experiencing one outcome in our reality while our other selves experience the alternative. This continuous branching creates an unimaginably vast multiverse, a tapestry woven with every possible quantum event. It's a world where every decision we make, every path we don't take, plays out in a parallel reality. While MWI remains a theoretical framework, it challenges us to expand our view of the cosmos. It suggests that our universe might not be the only one. Instead, we could be part of an infinitely larger and more complex reality than we ever imagined. Central to the concept of quantum immortality is the question of consciousness. How does our awareness, our sense of self, factor into this equation of branching universes? Does consciousness split along with the physical body, or does it somehow transcend the boundaries of individual realities? Some proponents of quantum immortality argue that consciousness is not confined to a single universe. They propose that our awareness, like a wave, might propagate through these branching realities, experiencing a continuous existence even as our physical bodies cease to exist in some timelines. This idea challenges our traditional understanding of the mind-body connection. It suggests that consciousness might not be solely a product of our physical brains, but could be a more fundamental aspect of reality itself. However, the nature of consciousness remains one of the greatest mysteries in science and philosophy. We don't fully understand how consciousness arises from the physical matter of our brains, let alone how it might interact with parallel universes. Despite the lack of definitive answers, the concept of quantum immortality pushes us to confront these profound questions. It forces us to consider the possibility that our consciousness, our very essence, might be far more resilient and interconnected than we ever imagined. The many worlds interpretation, if true, has profound implications for our understanding of reality. It challenges the notion of a single, objective reality and suggests that our universe is just one among an infinite number of parallel worlds. This concept upends our traditional view of cause and effect. If every possible outcome of every event exists in some universe, then does our concept of free will hold any meaning? Are we merely passengers on a predetermined journey through the multiverse? Are choices merely illusions? Philosophically, MWI aligns with modal realism, a view that considers all possible worlds as equally real. This perspective challenges the anthropocentric view of the universe, where our reality is considered the only true reality. However, the vastness and inaccessibility of these parallel worlds raise further questions. If we can't interact with or verify the existence of these other realities, are they truly real, or are they merely theoretical constructs? Despite these uncertainties, the possibility of a multiverse compels us to reconsider our place in the grand scheme of existence. It suggests that our reality, our experiences, might be just a tiny fraction of a much larger and more complex cosmic tapestry. Section 5. Ethical Considerations. Navigating a landscape of infinite choices. The concept of quantum immortality raises ethical dilemmas. If our actions have consequences in parallel universes, how do we navigate this moral landscape? Can we be held accountable for negative outcomes in one universe if there's a positive one in another? Does a positive impact in one universe absolve us of responsibility in another? If death isn't the end, does it diminish life's value in our reality? Does believing in another universe make us less likely to cherish life now? These questions challenge our moral frameworks. They force us to grapple with our actions' cosmic implications. Endless existence raises questions about life's meaning. Does living indefinitely diminish our current life's significance? Or does it grant us greater freedom to explore different paths? Section 6. The psychological weight of immortality, a blessing or a curse. While living forever might seem appealing, the reality of quantum immortality could be overwhelming. Imagine experiencing countless near-death experiences and witnessing diverging paths of your life. The knowledge of survival could lead to recklessness or detachment from the present moment. The fear of death might lose its significance, leading to apathy or nihilism. The accumulation of experiences and memories could become an unbearable burden. The sheer volume of information could lead to existential fatigue. Encountering different versions of ourselves raises intriguing psychological questions. How would we react to meeting alternate versions of ourselves? Would we feel a sense of connection or rivalry? The psychological implications of quantum immortality are complex and multifaceted. Endless existence presents profound challenges to our sense of self and our understanding of mortality. Section 7. The paradox of free will. Does choice exist in a predetermined multiverse? The concept of quantum immortality leads us to the debate on free will. If every possible outcome exists in some universe, does free will still make sense? In a multiverse where every possibility is realized, our choices might seem predetermined. If every decision already exists somewhere, what role does our choice play? This deterministic view can be unsettling. It challenges our sense of agency and control. Are we merely actors playing out a script, our choices illusions of free will? Some argue free will can still exist within MWI. Our conscious choices determine which outcomes we experience. Our choices still hold meaning, shaping our journey through the multiverse. The question of free will in quantum immortality remains complex and unresolved. It forces us to grapple with the nature of choice, consciousness, and reality. Section 8. Quantum immortality and the search for meaning. A new perspective on life and death. Quantum immortality, while speculative, offers a unique lens through which to examine the meaning of life and our relationship with death. It challenges our fear of mortality and invites us to consider the possibility of an existence beyond the confines of our current understanding. If death is not the end but a transition to another reality, it could profoundly impact our approach to living. It might encourage us to focus less on fearing death and more on living life to the fullest in the present moment. Furthermore, the concept of experiencing countless lives in parallel universes could provide a sense of comfort and hope. It suggests that even if we face hardship or loss in this life, there are other realities where things might unfold differently. However, this perspective also requires us to confront the potential for existential angst. The sheer vastness of the multiverse and the knowledge that our lives are but a tiny fraction of an infinitely larger reality could be overwhelming. Ultimately, whether quantum immortality provides solace or existential dread depends on our individual perspectives and beliefs. It challenges us to find meaning within the context of a potentially infinite and ever-branching reality. Section 9. The value of speculation. Fueling scientific and philosophical exploration. While quantum immortality remains a theoretical concept, the very act of contemplating such ideas holds immense value. Speculation, even when venturing into the realm of the improbable, plays a crucial role in advancing human knowledge and understanding. By exploring unconventional ideas like quantum immortality, we push the boundaries of our current understanding and open up new avenues for scientific inquiry. These thought experiments, even if they prove to be false, can lead to unexpected discoveries and breakthroughs. Furthermore, philosophical speculation about such concepts challenges our assumptions, broadens our perspectives, and helps us grapple with fundamental questions about the nature of reality, consciousness, and our place in the cosmos. The pursuit of knowledge thrives on curiosity and a willingness to entertain unconventional ideas. While we may never definitively prove or disprove the existence of quantum immortality, the journey of exploring such concepts enriches our understanding of the universe and our place within it. Section 10. Conclusion: Quantum Immortality. A Journey into the Heart of Existence. Quantum immortality, though deeply rooted in theoretical physics, extends far beyond the realm of equations and scientific models. It delves into the very essence of our being, forcing us to confront profound questions about consciousness, reality, and the meaning of existence. Whether or not this concept reflects the true nature of our universe remains to be seen. However, the journey of exploring such ideas is invaluable. It challenges our assumptions, expands our perspectives, and ignites our imagination. Quantum immortality reminds us that we are part of a vast and mysterious cosmos, a universe full of wonder and possibilities that extend far beyond the limits of our current understanding. It encourages us to embrace the unknown, to question our place in the grand scheme of things, and to never stop exploring the infinite frontiers of knowledge and imagination. The quest to unravel the mysteries of quantum immortality is ultimately a journey into the heart of existence itself. It is a journey that challenges us to confront our deepest fears and aspirations, to expand our understanding of the universe, and to embrace the profound beauty and mystery of the cosmos.
In our everyday lives, the laws of the universe feel comforting, simple, and reliable. These laws govern everything around us, from the flow of water to the motion of objects. Imagine standing by a river. You know the water will flow downhill. If you throw a stone into the air, you can easily predict the trajectory of its fall. Gravity, inertia, and motion are concepts we learn early in school, and they explain much of what we see. Similarly, when you heat a filament in a light bulb, it starts to glow. At first, it emits a dull red light, but as it gets hotter, the light shifts to a brighter orange, then yellow. These changes are predictable and follow the rules of classical physics, a framework that has guided human understanding for centuries. These laws make the universe feel logical, ordered, and accessible. But what happens when we look closer, much closer, into the microscopic building blocks of reality? At this level, the certainty we take for granted disappears, replaced by something almost incomprehensible. Welcome to the world of quantum mechanics, where the rules are not just different, they're bizarre. In this strange realm, particles of matter can exist in two places at once. Their behavior is dictated by probability rather than certainty, and their very existence seems to depend on whether or not they are being observed. Suddenly, the solid foundation of classical physics crumbles. A paradox emerges. For scientists, this was a shocking revelation. They had grown accustomed to a universe that operated predictably, where cause and effect reigned supreme. But at the smallest scales of matter, particles refused to follow these familiar rules. The more they explored, the more they realized that this microscopic world was unlike anything they had ever imagined. As one of the founding fathers of quantum mechanics, Niels Bohr, once said, "Everything we call real is made of things that cannot be regarded as real." In other words, the very fabric of reality, at its most fundamental level, defies our common sense. This discovery marked the beginning of a journey into the unknown, a journey that would challenge the very nature of our understanding of reality itself. The humble beginnings, a problem with the light bulb. At the turn of the 20th century, the light bulb was a symbol of progress, innovation, and modernity. It illuminated homes, powered industries, and revolutionized the way people lived. Yet, this seemingly simple invention posed a question that would baffle scientists for decades. Engineers of the time understood that when an electric current heated a filament, it glowed, producing light. However, the underlying physics of this process was a mystery. Why did the color of the light change as the filament got hotter? Why did it transition from red to orange, yellow, and white, but never to blue or ultraviolet, even at extremely high temperatures? This mystery became known as the ultraviolet catastrophe, a dramatic name for an equally dramatic problem. According to the classical physics of the time, as the filament's temperature increased, the intensity of light at higher frequencies, like ultraviolet, should grow infinitely. But in reality, this didn't happen. The filament emitted very little ultraviolet light, no matter how hot it became. This discrepancy wasn't just a minor annoyance for engineers, it was a fundamental challenge to the laws of physics. And it was here, in the pursuit of understanding the behavior of light in a light bulb, that the seeds of quantum mechanics were sown. Max Planck's revolutionary discovery. Enter Max Planck, a brilliant but pragmatic German physicist. In 1900, Planck was tasked with solving the problem of black-body radiation, the emission of light from an idealized object heated to a specific temperature. Planck proposed that energy is not emitted continuously, as classical physics suggested, but in discrete packets called quanta. These quanta were tiny, indivisible units of energy, and their size depended on the frequency of the radiation. At first, Planck saw this idea as a mathematical trick rather than a groundbreaking insight. He himself admitted that the concept was an act of desperation, a last resort to fit the experimental data. But the implications of his discovery were profound. Planck's work solved the problem of black-body radiation, but it raised more questions than it answered. Why was energy quantized? What did these quanta represent? And what did this mean for the nature of light and matter? The scientific community was intrigued but hesitant. Quantization seemed to violate everything they knew about the continuous nature of energy and waves. Yet, experimental evidence was undeniable. Slowly, Planck's radical idea began to gain traction. The concept of quantization didn't just explain black-body radiation, it challenged the very foundations of physics. If energy could exist in discrete packets, what else in the universe might be quantized? This realization opened the door to a new way of thinking, one that would soon reveal the true nature of light, electrons, and the building blocks of reality itself. But the journey was just beginning. Another phenomenon, equally puzzling, was about to push science even further into the quantum realm, the photoelectric effect. While Max Planck's discovery provided the theoretical framework for quantization, it was Albert Einstein who would take the next critical step. In 1905, Einstein applied the idea of quanta to light itself, explaining a phenomenon that classical physics couldn't, the photoelectric effect. This discovery would not only solidify the concept of quanta, but also earn Einstein the Nobel Prize. The photoelectric effect and Einstein's leap. At the turn of the 20th century, the scientific community was grappling with a phenomenon that defied explanation: the photoelectric effect. It was a simple enough observation. When light struck certain metals, it ejected electrons from the surface. Yet the process behaved in ways that were completely inconsistent with the classical wave theory of light. According to existing theories, light was a continuous wave, and its energy should depend solely on its intensity. A brighter light source, regardless of color, should transfer more energy to the metal, dislodging electrons more effectively. But experiments repeatedly proved otherwise. Red light, no matter how bright, could not knock electrons loose, while even a faint beam of ultraviolet light could do so effortlessly. Moreover, the ejection of electrons occurred instantly, as soon as the ultraviolet light made contact with the metal surface. This was baffling. If light behaved as a continuous wave, the energy should build up over time, like water gradually heating a kettle. But the reality was far different. In 1905, a young Albert Einstein proposed an idea that would revolutionize science. Building on Max Planck's earlier work on quantized energy, Einstein suggested that light was not a continuous wave, but a stream of discrete packets, or particles, which he called quanta. Today, we know them as photons. Each photon carried a specific amount of energy, determined by the frequency of the light. High-frequency light, such as ultraviolet, carried more energy per photon, while low-frequency light, like red light, carried less. This, Einstein argued, was the key to the photoelectric effect. When a photon struck the surface of a metal, it transferred its energy to an electron. If the photon's energy was high enough to overcome the electron's binding energy, the electron would be ejected from the metal. If not, no amount of additional photons or light intensity could dislodge the electron. This was why red light, even at high intensities, failed to knock electrons free, while ultraviolet light, despite its lower intensity, succeeded with ease. The process was instantaneous because it depended on a single collision between a photon and an electron, not on the gradual accumulation of energy. Einstein's explanation was as elegant as it was revolutionary. It resolved the mysteries of the photoelectric effect, but it also challenged long-standing beliefs about the nature of light. For centuries, scientists had debated whether light was a wave or a particle. Experiments with diffraction and interference clearly showed that light behaved like a wave. But now, Einstein's work revealed that light could also behave like a particle. This duality would become one of the defining features of quantum mechanics, reshaping our understanding of the universe. As we delve deeper into this story, we'll explore how these discoveries about light and matter transformed not just science, but our entire understanding of reality. The paradoxes of the quantum world, from wave-particle duality to the nature of measurement and observation, would become the focus of intense debate and groundbreaking research. These ideas would lead to experiments that defied logic, challenged intuition, and ultimately changed the course of human knowledge. Wave-particle duality of matter and light. The idea that light exhibits both wave-like and particle-like properties was revolutionary, but it was only the beginning. What if this strange duality wasn't unique to light? What if the fundamental particles of matter also behaved in ways that defied conventional understanding? This question led to one of the most iconic experiments in the history of physics, an experiment that forever changed our perception of reality, the double-slit experiment. In classical physics, matter and light were thought to be fundamentally different. Matter consisted of particles, tiny and indivisible, like billiard balls. Light, on the other hand, was a wave, spreading out through space like ripples on the surface of a pond. But as scientists delved deeper into the quantum realm, these distinctions began to blur. The double-slit experiment, first performed with light in the early 1800s by Thomas Young, was a cornerstone of wave theory. In this experiment, light passed through two parallel slits and created an interference pattern of alternating bright and dark bands on a screen behind the slits. This pattern could only be explained if light behaved as a wave, with the peaks and troughs of the waves interacting to either reinforce or cancel each other out. When light behaved like this, it was undeniable evidence of its wave-like nature. However, in the 20th century, scientists began to wonder if particles of matter, such as electrons, might produce a similar result. After all, if light could act as both a wave and a particle, why couldn't matter? To test this, researchers adapted the double-slit experiment for electrons, firing them one by one through the slits and onto a detection screen. At first, the results seemed straightforward. Each electron appeared on the screen as a single point, as one might expect from a particle. But as the experiment continued, a strange pattern began to emerge. When enough electrons had been fired through the slits, an interference pattern identical to the one produced by light waves appeared on the screen. This was astonishing. It was as if each individual electron, traveling through the slits one at a time, somehow passed through both slits simultaneously and interfered with itself. This behavior seemed impossible to explain. If electrons were particles, how could they produce an interference pattern? And if they were waves, how could they arrive at the screen as distinct points? The results defied classical logic, forcing physicists to confront the bizarre reality of quantum mechanics. Niels Bohr, one of the pioneers of quantum mechanics, embraced this idea. According to his Copenhagen interpretation, particles like electrons don't have definite properties or locations until they are observed. Instead, they exist as a cloud of probabilities, with the act of measurement collapsing those probabilities into a single reality. This interpretation was both elegant and unsettling, challenging the very nature of what we consider real. Albert Einstein, however, was deeply dissatisfied with this view. He famously asked, "Does the moon cease to exist when I stop looking at it?" For Einstein, the idea that reality depended on observation was unacceptable. He believed there must be hidden variables, underlying factors that determine the behavior of particles, but were simply unknown to scientists. This disagreement between Einstein and Bohr sparked decades of debate, with each defending their interpretation of quantum mechanics. The double-slit experiment and the concept of wave-particle duality have reshaped our understanding of reality. They challenge the classical view of a deterministic universe where everything follows a predictable path. Instead, the quantum world is governed by probabilities, superpositions, and entanglements, where particles can be connected across vast distances and time itself seems malleable. For many, these ideas are unsettling, even disturbing. They force us to confront the limits of human understanding and question the very nature of existence. Yet they are also a source of wonder and inspiration, revealing a universe far more complex and fascinating than we ever imagined. The journey into the quantum realm is far from over. With each experiment, we uncover new layers of mystery, challenging our assumptions and expanding the boundaries of knowledge. As we continue to explore the strange and beautiful world of quantum mechanics, we are reminded of one of the most profound truths of science. The more we learn, the more we realize how much we don't know. Quantum entanglement and Einstein's objections. The quantum world is a place of endless surprises, but few discoveries have been as mind-bending as the phenomenon of quantum entanglement. At its heart, entanglement is a mysterious connection between particles, one that defies all conventional notions of space and time. For Albert Einstein, this was a step too far, a challenge not only to physics but to the very fabric of reality itself. Entanglement arises naturally in quantum mechanics. When two particles interact, their properties can become intertwined, so deeply connected that the state of one particle directly determines the state of the other, no matter how far apart they are. If you measure one particle and find it spinning in a certain direction, the other particle will instantly adopt a complementary spin, even if it's on the other side of the universe. This immediate connection between entangled particles seemed to imply faster-than-light communication, something Einstein famously called spooky action at a distance. In 1935, he collaborated with physicists Boris Podolsky and Nathan Rosen to publish a paper now known as the EPR paradox. In it, they outlined their objections to quantum mechanics, using a thought experiment to highlight the apparent absurdities of entanglement. Imagine two particles are created in a single event and then separated by a vast distance. According to quantum mechanics, measuring one particle instantly determines the state of the other. But how could this happen? How could one particle know what was happening to its twin without any communication? For Einstein and his colleagues, the only logical conclusion was that the particle's properties were predetermined, encoded at the moment of their creation. The EPR paradox sparked intense debate among physicists. Niels Bohr, a staunch defender of quantum mechanics, rejected the idea of hidden variables. He argued that entanglement didn't involve faster-than-light communication or pre-existing properties. Instead, it reflected the fundamental interconnectedness of the quantum world. In Bohr's view, the act of measurement didn't just reveal information about a particle, it actively shaped reality, collapsing the wave function into a definite state. This interpretation, known as the Copenhagen interpretation, was as radical as it was counterintuitive. It suggested that reality itself was not fixed but fluid, dependent on observation. For decades, the debate remained unresolved. Entanglement was a theoretical prediction, something that could be described mathematically, but not tested experimentally. It wasn't until the 1960s that a physicist named John Bell developed a way to settle the question once and for all. Bell's theorem provided a framework for testing whether hidden variables could explain the behavior of entangled particles. His work led to the development of Bell's inequalities, a set of mathematical relationships that any theory relying on hidden variables would have to obey. In the 1970s, physicists began conducting experiments to test Bell's inequalities, using advanced technology to create and measure entangled particles. The results were astonishing. Time and again, the experiments violated Bell's inequalities, proving that hidden variables couldn't account for the behavior of entangled particles. Instead, the results confirmed the predictions of quantum mechanics, showing that entangled particles were indeed connected in a way that transcended space and time. These experiments had profound implications, not just for physics, but for our understanding of reality. They demonstrated that the universe is fundamentally non-local, meaning that events in one place can influence events in another, regardless of the distance between them. This non-locality isn't just a theoretical curiosity, it's a deeply ingrained feature of the quantum world. It challenges our classical intuition, forcing us to reconsider our notions of separateness and causality. For Einstein, the results were bittersweet. He lived to see his ideas about hidden variables discredited, but he never fully accepted the implications of entanglement. Until his death, he remained convinced that there must be a deeper, more intuitive explanation for the strange behavior of the quantum world. In his words, God does not play dice with the universe. But as the evidence mounted, it became clear that the universe was far stranger and far more fascinating than anyone had imagined. Entanglement isn't just a theoretical curiosity, it has real-world applications that are shaping the future of science and technology. Quantum cryptography, for example, uses entangled particles to create unbreakable codes. Because any attempt to intercept or measure the particles would disrupt their entanglement, it's impossible for eavesdroppers to access the information without being detected. This has the potential to revolutionize cybersecurity, providing a level of security that classical encryption methods can't match. Quantum entanglement is also the foundation of quantum computing, a field that promises to transform the way we process information. Unlike classical computers, which use bits to represent data as ones or zeros, quantum computers use qubits, which can exist in superpositions of both states simultaneously. Entangled qubits can perform complex calculations at incredible speeds, solving problems that would take classical computers millions of years to complete. From drug discovery to climate modeling, the potential applications of quantum computing are virtually limitless. But perhaps the most profound implication of entanglement is its challenge to our understanding of reality. In the classical world, objects are distinct and independent, each existing in its own place and time. But in the quantum world, entanglement blurs these boundaries, revealing a universe where everything is interconnected. This isn't just a philosophical abstraction, it's a measurable, testable fact, one that forces us to confront the limits of our intuition and embrace a new, more complex vision of the cosmos. Entanglement also raises intriguing questions about the nature of time and causality. In some interpretations of quantum mechanics, the connections between entangled particles suggest that the future can influence the past, or that time itself may be an emergent property rather than a fundamental feature of reality. These ideas are still the subject of intense debate, but they hint at a deeper, more mysterious layer of the universe, one that we are only beginning to explore. The story of quantum entanglement is a testament to the power of human curiosity. It began as a thought experiment, a challenge to the foundations of physics, and grew into one of the most exciting frontiers of modern science. It has taught us that the universe is not as simple as it seems, that reality is not always intuitive, and that the act of observing the world can change it in ways we are only starting to understand. As we continue to unravel the mysteries of the quantum realm, we are reminded of the words of physicist Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. This isn't a statement of despair, but a celebration of the unknown. It's an invitation to keep asking questions, to keep probing the edges of knowledge, and to embrace the wonder of a universe that is far more complex and beautiful than we ever imagined. Quantum superposition and its implications. The concept of quantum superposition stands as one of the most bewildering and fascinating ideas in the realm of quantum mechanics. It challenges the very essence of what we think we know about existence, forcing us to accept a reality where particles can exist in multiple states simultaneously until they are observed. This idea is not just theoretical. It has been experimentally confirmed and has led to technological advancements that are reshaping the modern world. To understand quantum superposition, consider a single electron. In classical physics, the electron is like a tiny marble that occupies a specific position at any given time. But in the quantum world, the electron doesn't have a single definite location. Instead, it exists as a cloud of probabilities, representing all the possible places it could be. This is what physicists refer to as a superposition. Until we measure the electron, it is not in one place or another. It is everywhere it could potentially be, all at once. One of the most famous thought experiments illustrating superposition is Schrödinger's cat, proposed by Austrian physicist Erwin Schrödinger in 1935. Imagine a cat placed inside a sealed box containing a radioactive atom, a Geiger counter, a vial of poison, and a mechanism that releases the poison if the Geiger counter detects radiation. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the system, the atom is in a superposition of decayed and undecayed states. This means the cat is simultaneously alive and dead, a chilling, paradoxical state that defies common sense. Schrödinger's cat was not meant to be a literal experiment, but rather a way to highlight the strangeness of quantum mechanics. It posed a profound question: does reality exist independently, or is it brought into being by observation? In the quantum world, the act of measurement collapses a superposition into a single outcome. Before observation, the system exists in all possible states. After observation, it snaps into one. This seemingly abstract concept has profound implications for how we understand reality. It suggests that the universe at its most fundamental level is not deterministic but probabilistic. The future is not preordained, it unfolds through a series of probabilities that solidify only when observed. For centuries, scientists believed in a clockwork universe, where every event followed inevitably from the one before it. Quantum superposition has shattered that view, replacing certainty with possibility. Superposition is not just a philosophical curiosity, it has practical applications that are driving some of the most exciting technological advancements of our time. At the forefront of this revolution is quantum computing, a field that leverages the principles of superposition to achieve computational power far beyond what is possible with classical computers. In a classical computer, information is stored in bits, which can be either 0 or 1. These bits form the foundation of every computation, from the simplest arithmetic to the most complex simulations. Quantum computers, however, use quantum bits or qubits. Unlike classical bits, qubits can exist in superpositions of 0 and 1 simultaneously. This means a single qubit can perform multiple calculations at once. When you combine multiple qubits, the computational possibilities grow exponentially. For example, with just 300 entangled qubits, a quantum computer could represent more states than there are atoms in the observable universe. Quantum superposition is also being explored in the emerging field of quantum sensing, which uses the delicate nature of quantum states to measure physical quantities with extreme precision. Quantum sensors are already being developed to detect gravitational waves, map underground structures, and monitor biological processes at the cellular level. These technologies promise to revolutionize fields ranging from geology to medicine, offering insights that were previously impossible to achieve. While the practical applications of superposition are impressive, the concept itself raises profound questions about the nature of reality. If particles can exist in multiple states at once, what does that say about the universe? Some physicists argue that superposition supports the idea of a multiverse, where every possible outcome of a quantum event exists in a separate, parallel universe. According to this interpretation, when we observe a particle and force it to collapse into a single state, we are not eliminating the other possibilities. Instead, we are choosing one branch of reality, while the other branches continue to exist in parallel. This multiverse interpretation is both thrilling and unsettling. Not everyone agrees with the multiverse interpretation, and the debate over the meaning of superposition is far from settled. Some physicists favor a more minimalist approach, arguing that superposition simply reflects the limits of our knowledge. In this view, the universe is not inherently probabilistic. It only appears that way because we lack the information to predict its behavior with certainty. Others, like proponents of the Copenhagen interpretation, embrace the idea that observation plays a fundamental role in shaping reality. Regardless of which interpretation is correct, the implications of quantum superposition are undeniable. It has forced us to abandon the comforting certainties of classical physics and embrace a world that is far stranger and more complex than we ever imagined. It has given rise to technologies that are transforming our lives and will continue to do so for decades to come. And it has challenged us to rethink our place in the universe, to question what it means to observe, to measure, and to exist. Quantum tunneling and its profound implications. In the macroscopic world, boundaries are solid and immovable. A ball cannot pass through a brick wall, no matter how hard it is thrown, and a car cannot drive through a closed garage door without destroying it. These everyday observations reinforce our understanding of impenetrable barriers, a concept deeply rooted in classical physics. However, the quantum realm defies this logic with a phenomenon so extraordinary that it challenges the very nature of reality: quantum tunneling. Quantum tunneling occurs when a particle passes through a barrier that, according to classical physics, it should not be able to cross. Imagine a ball rolling toward a hill. If the ball doesn't have enough energy to climb over the hill, it will roll back down. That's the classical view. In the quantum world, however, the ball doesn't always behave as expected. Sometimes it simply appears on the other side of the hill, as if it had tunneled through it. To understand why this happens, we must revisit the concept of quantum superposition. In the quantum world, particles such as electrons are not confined to a single location or state. Instead, they exist as a cloud of probabilities, simultaneously occupying many potential positions. When faced with a barrier, the particle's probability wave doesn't abruptly stop at the edge of the barrier. Instead, it extends beyond it. This means there's a small but non-zero chance that the particle can be found on the other side of the barrier, effectively bypassing the obstacle. One of the most significant applications of quantum tunneling is in semiconductors, the building blocks of modern electronics. Transistors, which power everything from smartphones to supercomputers, rely on the precise control of electron flow through barriers. Quantum tunneling enables electrons to pass through these barriers in a controlled manner, allowing transistors to function with incredible efficiency. This phenomenon is the foundation of the microchips that drive the digital age, making quantum tunneling an integral part of the technology that shapes our lives. Another groundbreaking application of quantum tunneling is in nuclear fusion, the process that powers the stars. In the core of the Sun, hydrogen nuclei fuse to form helium, releasing enormous amounts of energy. However, this process faces a significant challenge. The positively charged hydrogen nuclei repel each other due to their electric charge. Classically, they would need immense energy to overcome this repulsion and come close enough to fuse. Yet, in the Sun's relatively moderate conditions, fusion occurs at a rate sufficient to sustain its brilliance. This is possible because of quantum tunneling. The probability waves of the hydrogen nuclei overlap, allowing them to tunnel through the repulsive barrier and achieve fusion. Without quantum tunneling, the stars in the night sky would not shine, and life as we know it would not exist. One of the most fascinating aspects of quantum tunneling is its connection to time. In classical physics, the passage of time is a continuous, linear progression. However, experiments involving quantum tunneling have revealed hints that time may behave differently at the quantum level. For instance, researchers have observed that particles appear to tunnel through barriers almost instantaneously, as if time itself were compressed during the process. This has led some physicists to speculate that quantum tunneling could offer insights into the nature of time, potentially shedding light on some of the deepest mysteries of the cosmos. Quantum tunneling has also inspired bold new theories about the universe's origins. Some physicists propose that the universe itself may have come into existence through a form of quantum tunneling. According to this idea, the universe emerged from a quantum fluctuation in a vacuum, tunneling through an energy barrier into existence. This theory, known as quantum cosmology, suggests that the same principles governing the behavior of subatomic particles might also apply on the grandest scales imaginable. As we delve deeper into the quantum realm, we are confronted with a universe that is far stranger and more wondrous than we ever imagined. Quantum tunneling is not just a scientific phenomenon. It is a glimpse into a reality where the impossible becomes possible, where particles transcend boundaries, and where the mysteries of existence continue to inspire and astonish us. From quantum theory to breakthrough technologies, quantum mechanics has long been a cornerstone of technological advancement, transcending its origins as a theoretical framework to revolutionize industries and reshape human understanding of the physical world. Today, its applications permeate nearly every aspect of modern life, from the devices we use to communicate to the tools that enable cutting-edge scientific discoveries. One of the most significant contributions of quantum mechanics is the laser, a device that manipulates photons with extraordinary precision. Lasers have transformed medicine through advanced surgical techniques, powered telecommunications with fiber optic networks, and revolutionized manufacturing with precision cutting and welding. Similarly, quantum mechanics underpins the development of semiconductors, the foundation of modern electronics. Without the principles of quantum physics, the transistors that drive computers, smartphones, and countless other devices would not exist. Quantum computing is another transformative technology rooted in quantum mechanics. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers leverage qubits that exist in a superposition of states. This allows them to perform complex calculations exponentially faster than classical systems, opening new frontiers in fields like cryptography, materials science, and drug discovery. Quantum mechanics has also paved the way for advanced imaging technologies like MRI, magnetic resonance imaging, which rely on the quantum behavior of atomic nuclei in magnetic fields to produce detailed images of the human body. These technologies have saved countless lives and continue to push the boundaries of medical science. As we delve deeper into the quantum realm, the possibilities for practical applications only expand. From quantum-enhanced sensors that can detect gravitational waves to advanced quantum networks that promise instantaneous communication across the globe, the influence of quantum mechanics on technology and society is boundless. The practical applications of quantum mechanics have already transformed the world, but its greatest promise lies in the questions it raises. As we explore the quantum realm, we are not just uncovering the secrets of the atom, we are gaining insights into the nature of life, the cosmos, and our place within it. Will quantum physics prove to be the driving force behind the evolution of life? While the answer remains uncertain, one thing is clear: quantum mechanics is a key to unlocking the deepest mysteries of the universe. It is a testament to humanity's boundless curiosity and our relentless quest to understand the world around us. As we look to the future, quantum mechanics will continue to inspire, challenge, and guide us, shaping the technologies, ideas, and philosophies that define the next chapter of human progress. The journey into the quantum world is far from over. It is just beginning.